Thanks. Hi, my name is Łukasz Kąkol, and I will speak about performance optimization and profiling. As an examples, I will use comparison of Pythonic code and patterns inherited from other languages like C, C++, Java.
Excuse me, can you make it louder a bit?
Yeah, I will try. Okay, let me introduce myself a bit. I'm working as a senior Python developer at STX Next. It's a Python software house located in Poland. I have also gave my talks at PyCon UK last year and PySS, which is a Python conference in San Sebastian in Spain. And I have also shared my knowledge during local meetups in Poznań in Poland. But what's most relevant for the topic, I'm really interested in performance optimizations and I'm really fascinated in it. Okay, let's check up the agenda. I will first introduce you shortly to the topic of the performance aspects. Then we would have a live demo. And then I will summarize the talk shortly, and at the end we would have some time for questions. But before we get started, let me get to know you a little bit better. Who have ever used any profiling tool? Okay. Who is using that frequently, like on daily basis in daily job? Okay, not that much. And who is just starting a journey in Python? Okay. And who has used any other languages than Python, like C, C++, Java? Oh, okay, that's much. Okay, so let's get started. What are the base aspects of performance? First of all, it's CPU. We all want our code to be as fast as possible. That's what our client and our end user most cares about. Google Statistics says that that more than the half of the users will abandon the website if it takes more than 3 seconds to load. And moreover, each single second cause customer satisfaction to drop by about 15% and conversion to drop by around 5 to 10%. Another thing is memory. The truth is that we don't care about the memory until we run out of it. And I must admit it's a fair approach, because why should we care about something that is not affecting us? But we should be still aware that any memory leak can affect our software. For example, on daily basis in testing environments, we don't use as much fixtures as we would have in production. So the scale makes a really difference here. Last factor is input-output operations. For example, database operations or file system, this may massively influence the first aspect, so the time of loading an application or running, but it also has another side effects. There are specific limitations on simultaneous input-output operations. For example, database has transactions which may log and hold each other. File system has limits on number of simultaneously open files. Moreover, some services like Google App Engine provides resources like database up to certain quota. Then each read and write to database over that limit costs you real money. What should we do to optimize our code in a good way? First, we have to plan and predict our approach, implementation and the data structure which we will use. and predict which one will give us the best results. Then we should profile our code. It would be good to provide a few proofs of concepts. Of course, if we can, we should use some fake data just to indicate which one would be the best. But that's not all. Once we ship our code, we should monitor the performance in a living ecosystem. Keep in mind that you will not be able to test each data set. You can be almost sure that your end user will have some edge case you could not invent on your testing environment. And note that this may be also related to the tech stack the user is using. Once you have production benchmarks collected, you should identify bottlenecks and quick wins. And it really depends on each specific case. You should then take a look into optimizing your code again. You should first look into quick wins and bottlenecks. But should we optimize everything? Of course not. There is no point in optimizing something that will give you like 5% gain, and it will cost you few weeks or even months of work. So about profiling tools, there are a lot of them available in PyPy. I will just introduce a few of them, which I will use during the demo. First one is cprofile. It's to inspect the CPU usage divided by functions. That's part of standard library, and it's most accurate of the available tools. Next one is memory profiler. That's a third-party library. It's available on PyPy. It's better than other options, but it's still not perfect. Results may vary a bit, which I will present you later during the demo. And it also takes some time to profile the memory. Next one is sys. It's built-in library. It provides us with a low-level operating system API, which we can use to inspect, for example, CPU usage of the process or the memory. And last tool is this. It's also built in our library. We can use it to disassemble the Python code and inspect it on lower level. Okay, so now it's time for demo. Is that font size okay? Yeah.
Bigger is always better.
Okay. Okay, so let's start with the first example. First, I will show you the usage of the tools I will use during the presentation. First one is the function which I will use to profile the CPU usage. So I'm creating the list. I'm creating the second list, and then I'm deleting the first list and returning the second list. Okay, and how do we profile it? We should import cprofile, then import the function which we will use, and provide it as a string. so it can get evaluated. Oops. Okay. All right. Okay. So we can see that 6 functions has been called during the execution of the main function. It took 0.02 seconds, and we got number of calls of each function. Here in the last column we have the file name, line number, and the function name. Yeah, we got the number of calls of that function. We have total time of all the calls. Then we got time per one single call, average time. Then we got cumulative time, which is from the start up to the end of this function. Yeah, and cumulative time per call. Okay. We can also pass some additional arguments to cprofile, but I will not do that for now. I just want to show you the simple cases of CPU profiling. Okay. Another tool which we can use for profiling CPU is timeit, but it's not so accurate as cprofile, mostly because of a garbage collector not being run in timeit. So let's run the second example. Okay, we got 1 second, 1.85 seconds. It's the time of running the 100 retries on this example. So what we provide here is the real function to measure and the setup string, which also will be evaluated before running the real function to profile. Timeit is also available with the -m timeit. Then we should provide the setup string. And then the string with the real function to profile. This will give us a bit more readable result. So we got the information that we have run 100 loops. Best of 3 of these loops is 18.5 milliseconds. And we have also nice plugin for timeit in IPython. We should just import the function. And then we use %sign timeit CPU profile. And here we will have even more user-friendly way of showing the results. We will also have the standard deviation. Yeah, so we got average time here, and then the standard deviation here. It has been run in 100 loops, and it has been run 7 times. Okay, so that's about the performance, CPU performance. Now let's go to the memory profiling. So on the function, we need to profile. We should call the decorator. We should import memory profiler first, then use the profile decorator from this library, and we have a few optional parameters like precision. Yeah, that takes a bit longer. It probes the memory usage of the process after each line. So here we got the code we're profiling. We got the starting memory usage. And we got increment and the total memory usage here. So here we can see that first list took about 1.85 megabytes, second one took 1.87 megabytes, and then when we release actually the list A, we get back 1 megabyte of memory. What that may mean? Garbage collector didn't run yet, or there is one more thing. Some small integers are being cached by Python. So these are just few of the reasons, but there are definitely more. And moreover, there is we should also keep in mind that it's just probing, so it might not be 100% accurate. Okay. Another example will be greatest common divider. So we will disassemble it and see what the result will be. Okay. All these codes are listed in documentation of this library. So we got here we're setting up the loop. We're loading the y variable. Then if y is false, we will jump to line 24, so over here. Okay, in next line, we're loading x and y. We're calling binary modulo function. Then we store it in temp variable. Next line is assignment of y to x. So we're loading y and storing it in x. Next line is assignment of temp to y. We're loading temp and storing y, and we got the end of the loop. So we're jumping back to the second line over here. And then we're loading x and returning it. So that's the simple example of disassembled Python code. We'll also use it later for more interesting examples. Okay, another thing is another thing I want to talk about is the reliability of profiling. So we will call both CPU profiling and memory profiling 3 times and see the results. Yeah, note that we got 3 different times. Keep in mind that it might depend on many factors like another processes being run in the background. I tried to isolate that virtual machine as much as I could, but it still differs between the calls. About the memory, we also got different results here. First reason behind it is, as I said before, Python caching, and it's mostly visible in difference between first call and the other tools. So here we got different result, and here we got the same result at the end. The increment still differs, but it's because of caching in Python. Okay, another example is creating lists by list comprehension, by appending the result, and by extending the list. So definitely the fastest is list comprehension. Then 4 times slower is creating list by appending each subsequent item. And a bit faster is extending the list. So whether you would have the possibility to extend, use it, because it's a small gain, but in the scale it can really differ. Next example is a comparison of data types, tuples, lists, sets, and dictionaries. So the fastest is the list. Then we got sets. Tuple is much slower than list and set. And dictionary is even more slower, is the slowest of these collections, but we should keep in mind that dictionaries are keys and values pairs, so the construction of it takes time. Moreover, there is a hashing function which is hashing the keys, and we can see also the size of these collections. So smallest one is tuple, then we got list, set, and dictionary. Set is much larger than tuples and the lists. It's almost 4 times larger. But the reason behind it is that it's just optimized dictionary in the implementation. So it just have keys and dummy values, and is using just the keys of the dictionary, and that's how set is implemented. Okay, next example is using the values of the 2 lists, iterating by indexes, zip function, and using a dictionary. So zip function is the fastest one, then we got dictionary, and then we got iterating using indexes of 2 lists. So zip looks like the best option, but it's really not so usable in most cases, but dictionary is still fine. Next example is checking if element is contained within the list. So first one is just in keyword. Second one is running through all the list and checking if the element is present. And the last case is binary search over the list. So we're splitting the list in two equal parts and comparing if the element is present in left or in the right part of the list, then doing that recursively. Note that list must be sorted before running that operation. So I compare all these checks for two cases. First one is a positive case, so we will find this element in the list, and second one is that we will not find this element in the list. Okay, so first one is in keyword. So we can see that it runs 2 times slower if element is not present in the list. So the implementation here is a bit optimized for loop over the elements. Then we can see the for loop over the elements implemented in Python. It's in positive case, that's 1.6 seconds, and for loop is 2.5 seconds. And it also keeps the trend of positive to negative ratio. So it's still 2 times slower. And last one, binary search. It's definitely the fastest one. So in keyword is a Pythonic way to check if element is present. But if we really care about performance and really need to run it fast, binary search is the best option here. Even if the implementation is more complex, but it's still not that scary, right? It's just less than 15 lines. So if we really care about performance, we should use more complex solutions, but which are more efficient. Okay, next one is swapping the variables. First example shows swapping using temporary variable, and second one is swapping tuple. So assigning tuple of yx to xy. Okay, so swapping using temporary variable appear to be faster now. Okay, that's not what I expected. That might be some process running in the background which is interrupting that. Yeah, again, but different is not so big now. Probably if I run it again, it will finally give expected results. No, yeah, it finally gives the smaller value for swapping tuples. So let's see how it looks in disassembled code. We got here it's swapping tuples. So we're loading x and y and x. Then rotating these two, storing x and storing y, and then returning known. While here we got load fast, store fast, load fast, store fast, and again load fast, store fast. It's 3 times load and store instead of 2 store and load and store. Next example is efficiency of string construction. First one is fstring introduced in Python 3.6. Next one is formatted string, and the last one is percent formatted string. So f-strings are definitely fastest. Then we see that percent formatted strings are in the middle, and format is longest. Yeah, it's nice to use, but it's slow. But now in Python 3.6 we got f-strings, so let's use it. Okay, so we got nested loop here, and what I will do is iterate over the smaller portion of data in outer loop, then iterate over larger amount of data in outer loop, and then split it equally between outer and inner loop. So in all these cases, we got the same number of iterations. Okay, so maybe let's guess which one will be the fastest. So the first example, who thinks that it will be the fastest? Okay, second example. Okay, and the last one? Okay. Not everyone plays a bet, but okay, let's run it. Okay, so this one is the fastest one, so second one. So iterating over more items in outer loop, which I will expect otherwise, but it's appear it's not. Yeah, and there is not much difference between the first and the last example. Yeah, let's see at the disassembled code, because it may explain a bit more. So here we're starting first outer loop. Here we're starting inner loop. Here we're finishing the inner loop, and here we're finishing outer loop. So it's really what we would expect is that iterations over inner loop would be faster, but it appears that the iteration over outer loop is faster. Why is that? Because here we're jumping to the inner loop, and here we're jumping to outer loop. So if we jump over here frequently, it's a bit slower than jumping over here. Not sure if that's if that explains it, but yeah, it's pretty hard to explain on that disassembled code. But the fact is that more loops in outer loop is more efficient than in the inner loop. Okay, next example. Using global variable versus using parameter. So again, who thinks that global variable would be more efficient? Okay, who thinks that parameterized variable would be more efficient? Okay, let's see. We're frequently using the global variable, but it's not so efficient as parameterized version. We will see the reason over here in disassembled code. So the only difference here is that in global variable is loaded with load global instead of load fast over here. So that's the only difference, and it appears twice where we load this global variable or x parameter of the function. Okay. Next example is slots. Who is familiar with slots? Okay, so I will explain it a bit deeper. So slots are the listed parameter names that object will be restricted to. So if we got slots x over here, we cannot dynamically assign self.y, for example. It will just throw the runtime error. We will not be able to do that. Okay, so, but that sounds like a restriction for us, but what does it mean from performance point of view? It's definitely faster with slots, and as we will see in the second, it consumes a much less memory than just the regular object without slots. So we can see that it's 3 times more memory here used. The reason behind it is that objects without slots will over-allocate the memory, so that we can see it over here. It's 3 times more. That may, of course, differ based on different number of slots. If we, for example, give here like five variable names or 10, it will differ. Okay, so that will be all from demo part. Let's summarize it shortly. Okay, so first, predict what would be the best solution based on your experience, based on the examples you just saw, or just based on your hunch. Predict, but to have preliminary data, and don't trust it at all. Always profile your code. Predictions might be misleading. When I was preparing examples for this demo, I encountered a lot of surprises. We have also seen one. I have to rerun this 3 times because data was not perfect enough, I would say. So things do not behave as we expect. Yeah, we should always profile our code, even if you think it's fast enough or fastest. Just check it for your own peace of mind, right? And the last thing, calculate return on investment. So try to find the best ratio between possible profit and optimization cost. There is no point in spending weeks on optimization, which will give you unnoticeable improvement. Okay, thank you for your attention. You can find slides on the left side within the link or QR code. I will also put it on the EuroPython website. I have also pushed the code snippets to GitHub. Link is also available here. Its repository is private for now. I will make it public right after the talk. And I will also appreciate any feedback about my talk so I can improve myself to give better talks. There is a link on the right side to the feedback form. It's simple anonymous form. I would really appreciate if you spend a few seconds to share your opinion. Thank you very much.
Thank you, Łukasz. So we have time for a couple of questions. I see the hands.
Thank you for the talk. I was wondering, is there any easy way in C Profiler to give kind of like a person stats? So there was total time, there was cumulative time. Is there anything where you just give a parameter so that one line or one allocation took, let's say, 80% of the total time, something like that? Just not to calculate the whole thing.
Yeah, so that might be not so visible in the examples, but there is total time of all the calls or total time of or time per call for the function. You can also give a parameter to cProfile to sort the results by specific column.
Okay.
So we can sort by total time or time per call.
And also one short question. So in terms of that slot, your example didn't allocate anything to a particular slot. So let's say if you allocate 100 megs or like read a file of the same size with slot and without slot, do you think will make a difference?
Yeah, definitely. Because it's always good to profile the specific case because that depends what you're putting in this variable. But in general, object without slot is over allocated. So it will just allocate some memory right after the object to have some space to some dynamic assignments.
Thank you.
Who's okay?
I've got two questions actually. The first one is: are there any graphic tools for the profiling libraries you've shown?
Yes, there are graphic tools. I didn't list them because I wanted just the simplest tool, which will be most accurate. But there are many tools. You can just Google it, and yeah, there are a lot of them. I checked like a week or 2 weeks ago. There were a lot of them.
All right, thanks. And the second question is, since the profiling you've shown us is not really reliable, or not 100% reliable, should we rerun it multiple times to get a better understanding of how the application performs?
Yeah. When I run the memory profiler a few times in the loop, for example, it stabilizes with the time. So first run is like a bit inaccurate, but then it stabilizes and gives at least the total memory usage on the stable level. Then increment also stabilize. Like we saw in the example with when I run 3 times the same function with memory profiler, total memory per process has stabilized in the second and third line, but increment still did not stabilize. But it will stabilize at some point, because it probes the memory by inserting the probes into the code.
Okay, we have to stop here. Thank you very much for your talk.